All right. I hope that everybody is super excited to keep going. All right, so this next part, I want you to remember that we are still in one-dimensional motion. So we are either moving in the horizontal position or we are going to add in the vertical position with this unit. All right, so we're not doing them at the same time. So we are either traveling from east to west or left to right, or we're traveling up and down, north and south. All right, we're not doing both at the same time. All right, so today we are going to be introduced to something called accelerated motion. Now, up until this point, we have only dealt with constant velocity. All right, so that constant velocity we have seen on these graphs as a straight diagonal line on a position versus time graph, and then a straight horizontal line on a velocity versus time graph. So now we're going to be changing that up. All right, so what you need to know is what acceleration actually is. So all acceleration is just our change in velocity over a unit of time. All right, so our equation for acceleration is equal to delta V over delta T. So remember we had velocity.
Seniors, this is another reminder to bring items for the service projects with your K-5 buddies tomorrow morning.
I love
also,
that so much.
You may wear your senior jerseys with your uniform tomorrow.
Great. All right, so remember with velocity, our equation was delta x over delta t. So remember that was the equation that you got, but you had to remember that you could break delta anything down into final minus initial. All right, so we have x final minus x initial over our time interval. Remember, that's the one that we use more times than not. You could have broken down not only position, but also time. That could be t final minus t initial. All right, so you have to remember that with all of these as well, because this equation is the only one that you are going to get. All right, so you have to remember that delta anything can be broken down into final minus initial. All right, so that delta V can be broken down into V final minus V initial over delta T. So this is the one, just like the blue one up there, this is the one that you are going to be using more times than not. Others that you can use as V final minus V initial over T final minus T initial. All right, or you could be given delta V and two different times. All right, so these are all just different equations, different forms of the equation that you have to know. All right, but what I really want you to pay attention is when you have acceleration happening. All right, so there are three ways that you can have accelerated motion. All right, the first one is whenever you are speeding up. The second one is slowing down. And then the third one is going to be changing direction. So because velocity is a vector quantity, that means that even if that magnitude is staying the same, so say you are on cruise control, all right, even if that magnitude, that speed part is staying the same, if you are changing velocity, that means that you still have acceleration. All right, so speeding up, slowing down, and changing direction are all forms of acceleration. All right, so the unit that we have for acceleration is a derived unit. So remember at the beginning we talked about the difference between base units and derived units. All right, so a derived unit is what occurs or what comes about after you have done math. All right, so after you have combined different units and you have multiple units put together. All right, so acceleration's unit is either meter per second or meters per second squared. You will actually see it written both ways, meters per second or meters per second squared. All right, well, how did we get to that point? Like, what does that even mean? All right, so if we have meters per second, all right, that's dividing with fractions. That is awful. So we want to simplify the best way we can. All right, so we know that if we are dividing by fractions, seconds is technically seconds over 1. So to simplify that, we're going to multiply by the reciprocal. So we are going to have meters per second times, we are going to flip that bottom fraction. So that's going to be 1 over seconds. So that would give us meters times 1, which is just meters, over seconds times seconds. Well, if we have second times seconds, that means we're going to have meters per second squared. All right, so that's where we actually get that unit from. All right, so once again, we talk about how acceleration is a vector quantity. So it's velocity over time. Velocity is a vector quantity, so acceleration is going to be a vector quantity. What I want you to do is, I don't love this one. All right, so we're kind of going to mark that out. Underneath this slide in your notes, I want you to, of course, it's not going to do it. All right, let's see if I can make a new note. New. Yay. All right, I want you to make 3 different columns. All right, I want you to make a velocity column, an acceleration column, and then a motion column. All right, so we're going to do plus, minus, plus or minus, and a 0 and a 0. For acceleration, we're going to have plus, minus, plus, 0, plus or minus, and then 0 right here. Okay, so we know that vector quantities always have directions. All right, so you have to pay attention to the directions of both velocity and acceleration to figure out what is actually happening in this motion. All right, so I want you to look at the first 2. All right, so we have a plus, a positive velocity and a positive acceleration. And then we have a negative velocity and a negative acceleration. All right, so whenever those 2 things match, whenever you have the same sign for velocity as you do for acceleration, both of those mean that you are, oh goodness, there we go. Both of those mean that you are speeding up. Okay, whenever you, remember that acceleration happens whenever you are speeding up, slowing down, or changing direction. So whenever the signs for your velocity and acceleration are the same, that means that you are speeding up. Now, you look at whatever the direction is for your velocity, the sign for your velocity, that tells you what direction you're going in. All right, so if you have 2 positives, that means that you're speeding up in the positive direction. All right, because a positive velocity means that you're going in the positive direction. You're always going to look at the direction from your velocity to figure out what direction that you're going. All right, so if you have 2 negatives, that does mean speeding up. That negative velocity tells us that we're going in the negative direction. All right, now if you look at the next set, all right, these are opposite. So we have a positive velocity with a negative acceleration, a negative velocity with a positive acceleration. So because those 2 things are opposite, that means that they or the object are slowing down. Both of those mean slowing down. All right, so whenever you have the same signs for both velocity and acceleration, you're speeding up. Opposite signs, you're slowing down. And again, you're always going to look at the sign for your velocity to figure out what direction you're going. All right, so because I have a positive velocity, that means I'm going in the positive direction. I have a negative velocity, that means I'm going in the negative direction. All right, now I want you to look at this next one. So we have a positive or a negative velocity with 0 acceleration. Well, that's everything that we have been doing up until this point. All right, so if I do not have acceleration, that means that I have constant velocity, and that positive or negative means that it could be in the positive or the negative direction, whatever we have. All right, so say my velocity is 0 and I have a positive or negative acceleration. All that means is that I am speeding up from rest. I am speeding up from rest. Now, this last one should be the absolute easiest. I have 0 velocity, 0 acceleration. That means that I am at rest. I am not moving at all. All right, so you need to keep this handy. We are going to be referring back to it, so please make sure that you keep it, put big stars around it, all that good stuff. We're going to go back over here. Oh, maybe? Okay. All right, so we have our new equation. So we know that acceleration is equal to velocity over time, our change in velocity over time. All right, let's try this one. We have Turner's treadmill runs with a velocity of negative 1.2 meters per second and speeds up at regular intervals during a half-hour workout. After 25 minutes, the treadmill has a velocity of negative 6.5 meters per second. I want to know what the average acceleration of the treadmill is during this period. All right, now remember, we are getting into these problems. So we always take all of our word problems and break them down just like we have puzzles. All right, we're going to break them down into their different little puzzle pieces. And the way that we do that is we use our guess method. All right, so the first thing that we're going to do is we are going to write out our givens. All right, so we have negative 1.2 meters per second. That is our first given. Now, we need to realize, hopefully we know that anything that is measured in meters per second is a type of velocity. That negative tells us that it's going in the negative direction. All right, now after 25 minutes is our next given. So minutes are a measurement of time, so that's my time interval. Now, one thing I'm hoping that you are realizing is that our minutes need to be turned into seconds. So we're just going to multiply that by 60. So we get 1,500 seconds. All right, so that's our delta T. That's our time interval. And then our last given is negative 6.5 meters per second. Now, once again, that is in meters per second. So we have another velocity. Well, now we have two different velocities, so hopefully a red flag is going up in your head, and that tells you that you have two different velocities, which means one is your initial and one is your final. So you have to figure out which one is which. All right, so the negative 1.2 meters per second is before, all right, the 25 minutes. All right, so that one's going to be our initial. After 25 minutes, the treadmill has a velocity of negative 6.5. All right, so that's going to be our final. All right, so what I have asked you, those are our three givens. All right, remember to use that guess method. So we have givens. U means unknown. That's what we're trying to solve for. So we're trying to solve for acceleration. So we write down acceleration with our question mark. E stands for equation. We know that acceleration is equal to delta V over delta T. Now, that's fantastic, but we don't have a delta V. We do have delta T, but we do have V final and V initial, so we need to break that down one step further. All right, we do not have to do any rearranging at this point, so we are going to now plug in our numbers. All right, so V final is negative 6.5 minus negative 1.2 over our delta T of 1500. All right, we're going to bring that up. That's going to give us negative 5.3 divided by 1500. And that is going to give us an average acceleration of negative 0.00353 meters per second squared. All right, so that's what I asked you to find. I asked you to find your acceleration. All right, but now I want you to interpret that. Like, I want you to figure out what that means. So this is our solution. That's our answer. All right, so what that means, so if we have velocities that are negative, that means they're going in the negative direction, and our acceleration is also negative. We have two like signs. That means that we are speeding up. In what direction? We look at those velocities in the negative direction. So what that is actually saying is that every single second, Turner is speeding up by 0.00353 meters per second in the negative direction. So that is how we would interpret that. All right, so let's try another one. A shuttle bus slows down with an average acceleration of negative 1.8 meters per second per second. How long does it take the bus to slow from 9 meters per second to a complete stop? All right, so again, we're using that guess method. So we write down our givens first. All right, so our first given I told you was an average acceleration. So acceleration is going to be negative 1.8 meters per second squared. All right, then our next one is 9.0 meters per second. All right, we know that meters per second is a form of velocity. Now, remember, velocity is a vector quantity, so we have to get a direction. I did not give you a direction here, so we assume that it's going in the positive direction. All right, now, I don't want you to miss this. This is not a numerical value for our given, but it is super important. All right, so it comes to a complete stop. All right, that means that our V final, because it came to a complete stop, is 0 meters per second. All right, so those are our three givens. Remember, 0 does not need a direction, but it always needs a unit. And then the next thing that I write is my unknown. How long? How long does it take the bus to slow down? So that means we're looking for our time interval. All right, so I've got all of my givens written down. I've got my unknown written down. The next step is to write our equation. We know acceleration is equal to our change in velocity over our change in time. Well, we're trying to get time by itself. This is the one that a lot of you struggle with. So please, please, please pay attention. If your given is in the denominator, the very first thing that you have to do is to get it out of the denominator. All right, so to get it out of the denominator, we have to multiply both sides by it. All right, we are not going to multiply both sides by delta V. That's not going to get rid of delta V. That's going to be delta V squared. All right, so to get rid or to get delta T out of the denominator, we have to multiply it on both sides. All right, so that's going to give me delta T times acceleration is equal to my change in velocity. Well, I'm still trying to solve for delta T. It's being multiplied by acceleration now, so I divide both sides by acceleration. So delta T is equal to delta V over acceleration. So I've rearranged my equation, but there's a problem because I don't have delta V, but I do have V final and V initial. So before I plug in my numbers, I'm going to break delta V down. So that's going to be V final minus V initial over our acceleration. All right, do not ever skip this part. Don't just get rid of one because it's 0. This is super important. So for this one, our V final was 0. So 0 minus a positive 9 meters per second over our acceleration of 1.8 meters per second squared. All right, so that 0 minus something is going to make that top one negative. So that top is going to be negative 9 divided by negative 1.8. And that should make sense because we're solving for time and we can never have a negative time. All right, so negative 9 divided by negative 1.8 should give us 5 seconds. So it took 5 seconds for the bus to slow down from 9 meters per second to a complete stop. All right, so just touching a little bit on graphing, All right, so we have been doing constant velocity. So let's go back to our other note. All right, so these are motion graphs. All right, so far we have position versus time. And in position versus time, we have 3 separate shapes for a graph. All right, we have a horizontal line. All right, then we have a straight diagonal. And then we have seen a curve. All right, remember that straight horizontal means that your object or your person is at rest. It's not moving. That straight diagonal line means constant motion, but this curved line now means that we have a change in velocity. This is a form of acceleration. So if we were to turn these into velocity versus time graphs, if we were to turn them into velocity versus time graphs, we would draw those T's. All right, all of these are velocity versus time. All right, this one would be no slope, and so it would be at 0. That is a constant velocity, and because it's going in the positive direction, it's going to be above that 0. Now, if we have acceleration, that means that our velocity is changing. So this one in particular means that it's going to be speeding up. So no longer are we looking at those horizontal lines for velocity versus time. We're now going to have a diagonal line. So that diagonal line means that we have acceleration. All right, but remember that diagonal line for position versus time meant constant velocity. This one, we've already talked about it. The slope of velocity versus time graphs give us acceleration. So if we have that straight diagonal line for a velocity versus time graph, we do have acceleration, but it is constant acceleration. All right, both of these have no acceleration. Okay, so what we are adding to is going to be acceleration versus time graphs. Okay, and don't freak out on me just yet. They are the exact same thing. All right, so for these, remember, they're going to be t-graphs, just like velocity. So for the first two, you have no slope, so there is no acceleration. So you're going to see that straight horizontal line on 0. Now with this one, it's going to be kind of the same. So if you look at this straight diagonal line on a position versus time graph, that turned, I don't know why that's going, I don't know. All right, that turned into a straight horizontal line. Well, it's going to do the same thing here. All right, that's going in the positive direction, so it's a positive slope, so it's going to be a positive acceleration. All right, so that is kind of your introduction to these accelerated motion graphs. So these are all of the new things that we have to look forward to. Yay, I'm so excited. All right, so let's go back. I think I just did like 2 of these. Yeah, I pretty much just did 2 of these. So this is graphing this motion on a velocity versus time graph. This would have been that curved motion on a position versus time graph. So this is the time that it is going to get extremely important for you to pay attention to what types of graphs you are looking at. All right, now I want you to do this one on your own. All right, so using the base equation for acceleration, so that's acceleration is equal to our change in velocity over our change in time. I want to figure out how to find the final velocity. I want to get v final by itself. So I want you to take this equation, rearrange it, and get v final by itself, and then come show me that tomorrow. Okay? So if y'all have any questions, I hope this wasn't too hard. I know that it's a lot of information, especially looking at those graphs, but I promise we're going to be doing a whole lot more with it. So if you do have any questions, then you know where to find me.